talk about, oops, concavity. So we have two types of concavity in math. Something that looks like this, we refer to it as concave up. So if it opens upwards, we define it as concave up. And it doesn't have to be like a full cup or something like that, right? If it's partial like this, it's still concave up. Or if it's partial like this, it's still concave up. Then we have the concave down, which looks like this. So if it opens downwards, then we say it's concave down. And it doesn't have to be full again. It could be partial. Whoops. It could be partial like this. That'd be concave down. Or it could be partial like this. So if we take a piece of it, it's concave down. Are we okay on this concavity thing? Not too complex. Does everyone understand what concavity is? Okay. Now what I want to draw your attention to is actually to the bottom of these concavities. So right here and or the top. At the bottom of that concavity, how would you classify that? Would that be a relative max for the concave up or a relative min? So for concave up, it's going to be a relatively min. And for concave down, it's going to be a relatively max. Now there's also something interesting about this and why it's called a second derivative test. When something is concave up, the second derivative is positive. So the second derivative is going to be greater than 0. And when it's concave down, the second derivative is going to be less than 0. Now, hopefully I haven't lost anyone yet. So concave up, we're going to have a relative min, and the second derivative is going to be greater than 0. Concave down, going to be a relative max, and the second derivative is going to be greater than 0. Now, sometimes these graphs looks like this. Now we can see that this is a relative max and this is a relative min from our previous section, right? What I'm interested in right now is this point right here, where the two curves join. You'll notice that the curve on the left side, this piece, is concave down. and the piece on the right side is concave up. Do we all agree with that? Now this point where the concavity changed from up to down or down to up has a special name. It is called the point of inflection. So this point of inflection is where f double prime of x is equal to 0. So it's where the second derivative is equal to 0, or where the second derivative does not exist. So it's kind of like the critical number, but it is for the second derivative. And fill up the homework from this section. So 3.2 is actually a short section. And you only have, I think, 8 questions, and I took out 1 last night because it's just way overboard. So it has 7 questions, but they have multiple parts, so they can be pretty long. And you do need to cover 3.1 and 3.2 to take the quiz. All right, so here we go. Question is, let's copy the instructions too. So we start off with them giving you the graph, just like we did previously in 3.1. And then eventually they're going to give us no graph and still ask us to do the same work. So this is actually problem number 1 in the homework. This is 3.2 number. Identify the point or points of inflection and identify the intervals where the function is concave up or concave down. So this is kind of similar to the one we just did. So we can make it better, bigger. So do we have any concavity up or down here or points of inflection? How about point of inflection? Can someone help me with this? Do we see any point of inflection? 0, 5? For so so Myrta, you're saying this point here, that's a point of inflection? Maybe. Maybe. Now 0, 4 is definitely relatively max, right? Now where's the point of inflection? The point of inflection is where it changes once again from concave up to concave down, or from concave down to concave up. Now the left side of this graph, is it concave up or down?
Concave up.
So the left side is concave up. I agree with you, right? So concave up looks like this, right? So that's concave up, and concave down looks like this, right? So the left side is concave up, and the right side is concave down. The question is, where does it change from concave up to concave down? Where does it go from this transition? This is a point we're looking for, not the relative max or min. The point of inflection is where it changes. So -1 and 3, which is right here. And I think that's correct, Cameron. So our point of inflection would be -1 and 3. Myrta, do you understand what we're saying? Are you okay with that? So we're looking for the point of inflection, right? If you look over here, so when we have a graph that looks like this, it's concave up. And when we have a graph that looks like this, it's concave down. No, this is the point we're interested in. That's the point of inflection. The point of inflection is where it changes from up to down, or down to up. So this is up and down. It's not the maximum or min. It's the point where it's changing concavity. Are you with me? Okay. So the point of inflection here would be -1 and 3. Now the concavity, where's the concave up? Where would that be? So this piece would be concave up in red, and this piece would be concave down in green. So what's the x values that it's concave up? All right, the concave -1 is where, so we're interested in domain, right? Which is the x values. X value is where it stops. So it does stop at -1 right here. It's -1 and 3. But what's the x values all the way out here? So that's what we're interested in. That's the interval. What are those x values? This would be from negative infinity to negative 1. Now the concave down would be from this region. What are the x values there? Negative 1 to infinity. I agree. Let me copy this problem. All right, so this is problem number 2. Now, this is what I'm talking about. They are exhausting, right? There's not a lot of problem, but it has multiple parts. This one has A, B, C, D, and E. Now, it says for the following function, let's do this. Give the coordinates of any critical numbers and classify each point as a relative max or a relative min, or neither. So that's the first part. We're in time, 7 minutes. Probably cannot finish this problem in 7 minutes, but let's get started. How do we find critical numbers? The first derivative, right? So we take the first derivative and we set it equal to 0. So that's going to be 6x squared minus 24. And if it's a fraction, we have to see where it also does not exist. So this becomes 6x squared is equal to 24, or x squared is equal to 4. So x is equal to plus or minus 2. So we have two critical numbers here. So that's the first point. Now, how do we know if this is a maximum or minimum? So we know these are the critical numbers. Well, we could go back to the first derivative test and find where it's increasing or decreasing. But we'll do the second derivative test. And the second derivative test says if f double prime of the critical numbers is greater than 0, which is what we have above when we talk about this, then it's a relative min, right? So it's much easier, and if f double prime of the critical numbers is less than 0, then we have a relative max. So what is this saying? It's saying we're going to plug the critical numbers into the second derivative. So what's the second derivative? H double prime of x would be equal to 12x. That's the second derivative. our critical numbers are once again negative 2 and 2. So we're going to plug these into the second derivative. So this would be 12 times negative 2, and this would be 12 times 2. So this is negative 24, and this is 24. Now, all we're interested in is actually the sign. So this is negative 24. Is that a max or a min? It's a min. So we know a negative 2, this is a min. And at 2, because it's positive, then we know it's a max. So we don't have to look at that interval stuff. That's the first derivative test. The bad thing is that the second derivative test does not always work. Right? We still need to find the points, because these are just, how do we find the y values? We plug it back into the original equation, right? So we have to find h of negative 2 and h of 2 to give us the y value here.